Hi, welcome to our channel Seriously Amazing. Today I'm going to talk about CP modeling of oil and gas platform in an offshore environment using aluminum anodes. This model is basically based on primary current distribution and stationary study, incorporating world-famous cathodic protection technique. The principle of cathodic protection using sacrificial anode is quite simple. The steel structure is electronically connected to a less noble metal, for example aluminum, which causes the aluminum, also known as sacrificial anode, to be anodically polarized and the steel structure to be cathodically polarized when the electrodes are immersed in seawater. The anodes are then dissolved through anodic dissolution of the metal, while oxygen reduction takes place at the surface of the steel structure. You can see the same phenomena in the photograph. Anodes and cathode. Anode is aluminum anode. Cathode is a platform connected via metallic path. And you can see here anode dissolves, sacrifices itself while protecting the platform or cathode. You can see the equation, while electrolyte or ionic path is known as the seawater in this case. For the current solution, platform is assumed to be covered by a cylindrical marine environment. This is our assumption, especially specifically for this case. You can see here platform is sitting right in the center of the cylinders, and this cylinder we have assumed acting as an electrolyte or surrounding environment. The radius of the inner circle is chosen so that the main part of the charge transport occurs within the circle in this circle. The outer cylinder, this one, is modeled as an infinite element domain, which rescales the equation to represent an approximately thousands times larger cylinder, as the sea is spread quite far away from the platform. So that's why we set this outer platform as an infinite element domain. In seawater, the composition is assumed to vary to a very small extent, and diffusion of the ions that carry the current is negligible compared to the contribution from migration of these ions in the electric field. Basically, this assumption, together with the boundary condition, allows using a primary current density distribution analysis on the system, where only the influence of ohmic effects in the given geometry are considered. Further to that, at the sacrificial anode surfaces, a constant potential is set, assuming a relatively fast kinetic. This assumption implies that a very well change in surface our potential leads to a very large change in current density, and it is therefore reasonable to set a constant potential. Grounding the electronic phase potential, setting it to zero. The boundary condition for the electrolyte phase potential is given below. For this case, the value of the equilibrium potential of the aluminum anode as a standard, as we all know that, is minus 1.05 volt with respect to silver chloride reference cell. That is what we have used in this model. This example is based on a recommended practice for cathodic protection designed by DNV RP B401, published in 2010. Further to that, at the steel surface, it is assumed that oxygen reduction takes place at a limiting current density, which is quite important factor. Limited to the limiting current density is limited to the rate of transport of dissolved oxygen to the steel surface, and that the steel surface is sufficiently protected so that metal dissolution currents can be neglected. This yields a constant normal current density boundary conditions at the steel surface of the structure. The boundary condition for the steel surface we have used in this model by default, described by this equation. Uh, for this solution, the value of the limiting current we have used 100 milliampere per meter square or 0.1 ampere per meter square, while all the other boundaries are insulated. The model can be easily extended to secondary current distribution analysis in order to add the kinetics of the electrode reaction in a second stage. So please do not forget to hit like, subscribe, and click on the bell icon to get notification for the advanced model of the oil and gas platform in coming days. So let's start with the model builder. So now you can see here a pre-imported platform geometry. So in this design or in this solution, we are going to draw some anodes and electrolyte around the structure, and then we'll analyze the solution and to see how it's going to perform and protect our steel structure, in this case oil and gas platform. So first of all, we'll define a name for the structure, and we call it as a platform. And now we'll create a discrete aluminum anodes around the structure. So let's start with creating cylindrical anodes having radius of 0.5 meter and length of 3 meter. So you can see here anode is hidden somewhere within the platform. You'll just relocate it. X minus 5. Yep, you can see here. And then we'll create an array of the anodes around the lower leg. We need 4 anodes having 6 meter separation, and this is our input object. You can see here 4 numbers of anode aligned with the lower leg of the platform. So in order to cover these parts of the platform, we'll just create and rotate command. And then we'll define angle of separation. In this case, 60 degrees. So next 120, 180, 140, and 300. Let's see. So you can see here 6 numbers of anode arrays around the lower part of the platform. Now we need to create anode for the upper part of the platform. We'll do the same, and we'll use the same anode dimensions for the upper part as well. 3 meter, x minus 13, and z plus 23 meter high from the bottom. So you can see here anode is there. Similarly, we will create an array of these anodes as well along the upper part of the platform. We need 9 anodes, 8 meter apart. Yep, the array is created. And again, you will rotate this array again around the upper part of the platform by using a rotate command. Now select all the anodes to be rotated, and for the upper part we are keeping them 90-degree apart. It is because of we have less surface area to cover for the upper part. You can see here 4 arrays of the anode along the upper part of the platform and 6 arrays of the anode we are going to use for the lower part of the platform. And then we need to define the name of the anode. So this we can do by creating a union of all the anodes. So there are other ways as well to select them and nominate them as an anode, but I feel it is handy for me at the moment. So you'll just define a name for all these domains, and now they are called anodes. Platform is there, anodes are there around the platform, and now we need to create an electrolyte environment resembling to the seawater environment around the platform. For that, let's create another cylinder of 40 meter radius and 100 meter height. So you can see here, this is where our charge transfer will take place. So let's create another cylinder of slightly bigger dimensions. So now we got two cylindrical electrolyte dimensions around the platform. As I defined during the initial phase of this session. The outer circle will be acting as an infinite element domain. This one. The radius of the inner cylinder is chosen so that the main part of the charge transport occurs within this cylinder. The outer cylinder is modeled as an infinite element domain. This one, which basically rescales the equation to represent an approximately thousands times larger cylinder, is to resemble the seawater around the platform, and it should look like cylindrical, so that's fine. I'll go back to the geometry and create a difference. By doing that, basically we will define the electrolyte part of the geometry and the solid part of the geometry. So here in this case, you want to keep this electrolyte domain and want to subtract the solid part of the geometry, which is in our case anode and platform, and we'll create a difference. So let's go to the material tab. So I'm just going to use a simple material for our electrolyte, and for this I'm going to use 0.3 ohm meter electrolyte resistivity, which is basically the reciprocal of the conductivity. That's what is defined here. So it is accepted. Now let's go to the primary current distribution. Since we're using primary, we can change it to secondary here as well, but we keep to the primary for this case. Secondly, we got physics tab. So by default in Comsol, the surface potential always measure against silver chloride reference electrode, and if you want to choose different reference electrode for your specific application, you can choose different reference electrode given here or anything else. Then we need to define electrode surface. So if we select it anodes from here, so you can see here all the anodes are now defined as electrode surface, and we assume all these anodes are connected to the structure via low resistive path, or in other words, I'll say that all these anodes are assumed to be directly connected to the structure. So that's why we don't need to add any external resistance here. So if you go to the boundary conditions, so all the boundaries of the anodes are selected. Since we are using aluminum anode, so we know that the open circuit potential of the aluminum anode is 1050 millivolts with respect to silver chloride reference electrode. That is what we have defined here. And then we will select another electrode surface for our platform. So now this platform is selected as another electrode surface. And here in this approach, we are going to use a fixed electrode current density, and the value I'm going to choose 100 milliampere per meter square. Be careful with the units. So whatever value you're using, please define a correct unit. Otherwise, system will just use default units and you will get unexpected results. So let's compute the solution. It will take some time to compute. So meanwhile, we can have a look of the geometry from different angles. Yeah, it is now computed, and you can see here electrolyte potential, how well the whole electrolyte is covered with potential vectors. The next step is define electrolyte current density. You can see here. So let's closely analyze one of the anodes. So you can see here current density is larger at the end of the anodes, and it is also larger towards this surface facing towards the platform. And the third tab is define electrode potential, uh, basically anode potentials, as we have choose aluminum anode. So we can see here all the anodes are active and exhibiting 1050 millivolts. So the unit is now shown here, minus 1.05 volts exhibited by the anodes. So let's create another 3D plot in order to see the surface potential profile of the platform. So we'll choose as negative values, selection, and then we will select the structure to be red. So now you can see here the solution or the surface profile of the steel structure in terms of surface potential with respect to silver chloride reference electrode. As we know that negative 800 millivolt with respect to silver chloride reference electrode is the acceptance criteria for a steel structure in an seawater environment. So which is here, and let us show the unit. Okay, so you can see the upper part of the platform is well protected, all in the green zone, and more negative than 800 millivolts. So we can basically see the actual value on that specific location of the platform by clicking on that. So if you click on this portion, you can see here it is polarized to 807 sorry, it is polarized to 878 millivolts. If we select the other one, 876 millivolts, see from the top, 871 millivolts, 850, and so on. On the same time, we can see here that the lower part of the anode is not fully protected, or in other words, it's underprotected. This is because of large surface area at the bottom part of the platform and some shielding effect as well. We are not getting fully protected polarized potential on those areas. So if you click on one of the leg here, you're getting 731 millivolts. So nothing to worry. This was our initial design for this specific application of the oil and gas platform. So basically this software, the Comsol, help us to visualize what we are thinking is going to work or not, and if it works, how it will look like. So this is exactly, you can see the whole platform in one blink of eye is there. So the lower potential level of the lower part of the platform can be improved by increasing the number of anode and selecting different location of the anode as well. So I think that is it for today. At the end, thanks for watching. I hope you liked the video. Please do not forget to hit like, subscribe and click on the bell icon button to get notifications for more interesting CP models of the steel structure in near future. Thanks again. Bye.